off their school assignment and started playing video games next door. All right, so let's talk about mercuric ion catalyzed hydration of alkynes. This reaction involves a ton of equilibrium steps. Lots of proton transfers. So the pi bond is a nucleophile again, as always. But mercuric sulfate is actually discrete ions in solution. It's the mercuric 2+ ion and the SO4 2-. It isn't partially covalent the way the mercuric acetate is. So we got the mercury 2+ ion, and it gets attacked. It still has a lone pair of electrons on it, though, because it still has that D10 electron configuration. So we're going to go through a 3-member ring intermediate where there's 2 positive charges in the ring, kind of distributed between the 2 carbons and the mercury, right? So it's a mercurinium ion, but it's a mercurinium ion that still has the pi bond between the 2. Right? So this is nucleophilic attack of the pi bond on the electrophilic mercury. Mercuric ion. That's not very stable. That 3-membered ring is particularly unstable because we've got the pi bond in there as well. So water can attack, and it pretty much mirrors the attack of the mercurinium ion from the oxymercuration demercuration, where water comes in and attacks the more substituted end to open the ring. Right, so no surprises really. And now we have H2 on there. And there's an extra hydrogen there that shouldn't have been there. So now we've got 1 positive charge on the oxygen of the water, and that hydrogen's not there either, because I'm an idiot. And 1 positive charge on the mercury. So the positive charge is spread out a little bit. Now we're going to do a series of proton transfer reactions. We need to take the hydrogen off the oxonium ion to generate neutral OH. Right. So we've succeeded in doing the same thing, kind of analogous to what we did with the oxymercuration demercuration reaction, where we've added the electrophilic mercury to one side and the nucleophilic water to the other side of the triple bond. But when you have an alkyne, it doesn't stop because we still have a nucleophilic pi bond. So that nucleophilic pi bond can attack the hydronium ion, which is in there because we have sulfuric acid. Right, it's another proton transfer reaction. Step 4. And this is just like what would happen from the ordinary hydration of a pi bond, where you get carbocation rearrangements. But this time, this carbocation is not subject to rearrangement because the carbocation is stabilized by resonance. So it doesn't need to do a rearrangement. The rearranged carbocation would not be stabilized by resonance. So this is actually the most stable carbocation because of the resonance. tertiary carbocation, in this case, is less stable than the secondary carbocation with the hydroxide. Now what happens is mercury just falls off, right? It gives up this pair of electrons because mercury 2 plus is pretty stable, and pushes the pair of electrons back on to pushes that pair of electrons back onto the OH to generate the pi bond. And that's why this reaction is catalytic in mercury as opposed to stoichiometry, where the oxymercuration, demercuration is stoichiometric and the mercury stays attached. So that mercury 2 plus can now go in and attach. This is what's called an enol, and enols are unstable, and they will do what's called a tautomerization, to the more stable keto form. So that's a two-step reaction where the hydrogen is going to come off the oxygen and go on to the carbon. And that reaction occurs anytime you have an enol. It doesn't have to have been generated from this oxymercuration reaction. Anytime you have an enol in the presence of acid, it's going to rearrange by protonating the carbon and then deprotonating at oxygen. And again, the intermediate carbocation is stabilized by resonance because the pair of electrons on the oxygen can go in to form the pi bond. And then in step 2, we're going to deprotonate at oxygen. And it doesn't matter if you show the deprotonation happening from this resonance structure or from that resonance structure, as long as you show one of these pairs of electrons going in to form the pi bond. So that generates the ketone. That's the keto-enol tautomerism, and you'll see it again in chapter 17. And that's why you always want to avoid, in the answer to spectroscopy problems, putting a hydroxyl group on a pi bond like that. The hydroxyl group on the pi bond is unstable. It can also be catalyzed by base. You would just do these steps in the reverse order. You would deprotonate at oxygen first to generate an alkoxide, and then protonate at carbon. Right? So this is the keto-enol tautomerism, step 1 and step 2 of the keto-enol tautomerism, step 6 and step 7 if you're going through the entire mechanism, right? Because mercury falls off in step 5. So it's a lot of proton, or in this case mercury, either being attached to the pi bond or coming off the pi bond.